Hey, 12th graders. We are on 14.3 today, and we're really starting to lean into this idea of area under a curve. So, what we've done so far with our integrals is we've talked about integrals as a backwards of derivation of derivatives. And we've talked about it as this like tool that now we can apply all of the things that we learned with derivatives. And now there's just this like one more step that we've added in that we can use if we wanted to go backwards with any of those relationships, whether we're talking about velocity, acceleration, and time, or whether we're talking about the tangent line. And man, it would be really nice if we had the original equation. And so now we have that tool to be able to go back to go find that original equation when we only have the derivative. But we have talked a little bit about the fact that your derivative, or sorry, your integral is just the area underneath your curve. And the last two lessons of this unit go really deeply into that. We're going to end with something called the trapezoidal rule, but this is leading into that first. So this is just kind of your first baby steps into it. It's not learning any new mathematics. It's just kind of getting a grasp on the idea here of what this is. So this object is traveling at a constant velocity of 8 kilometers per hour for 4 hours, and then it travels for a further 2 hours with a steadily decreasing velocity until it reaches 0 kilometers per hour. So, if we were given a problem that looks like this, and I would ask you, explain to me a story that would go with this. Why would you be going at a constant speed and then your speed decreases? So, actually, let's go ahead and take a moment right now, and I would like for you to write a little short story about what type of situation could be a speed that's constant and then it slows down. So maybe you talked about a car, how a car was at a constant speed, and then maybe it got close to home, and then it slowed down, or maybe it was approaching a light, and so it steadily decreased its speed. It could also be a particle. Maybe if it was a particle that was at a constant speed of 8 kilometers per hour is a very fast particle, but it could be, or a very slow particle, I guess, depending on what you're thinking about. But you could have a particle that's going like 8 kilometers per hour, and then maybe because the temperature is getting colder, its speed decreases, which is like a familiar relationship, hopefully for those of us who are in chemistry. So there could be all sorts of different relationships here that would have this. It doesn't just have to be a car or a person. It could be particles. It could be the velocity rate of growth, but there could be a lot of things here. So, what distance did this object travel during its entire journey? And so, if we're given velocity and time and we're asked to find distance, normally we would set up the relationship of distance is equal to speed times time. And your speed is your velocity, and your time is this guy right down here on the x axis. So, if we wanted to find that number, it's fantastic as long as we have a constant for your speed and a constant for your time. As long as it is one number for speed and one number for time, it's super easy to solve for that distance. Now we have a part of this graph where your speed is consistent. It is constant. Your speed is 8 kilometers per hour for 4 hours. Okay, so we could find that part of the distance traveled, right? If we wanted to do the first part, it would be okay, well, speed equals 8 and time equals 4. So then let's keep in units here because that's going to be something that we need to be a little bit more familiar with than we have in the past. So then our distance is going to be 8 kilometers over hours times 4 hours. Notice that that's hours over 1, right? So if you did 8 times 4, well, that's equal to 32. And if we want to know the unit of measurement for that guy, if we take a step back and think about it, it's kilometers. But how we would know it if it's a more complicated problem, which even your check for understanding for this guy is going to be a little bit more complicated, that the hours down here and the hours up here cancel out. And so all you're left with is kilometers. So that's how you know for sure that the unit of measurement is kilometers. All right. Well, that's great. That's the distance for the first 4 hours, but we don't really know what the distance is for the rest of these 2 hours. Now, if we think about the fact that we just multiplied 8 by 4 in regards to the geometry of this problem, we just found this rectangular area that's split if I were to draw down a split between that diagram, right? We just found the area of this space for that specific amount of time. So our second distance, our second distance is a little bit harder to come by. Our second distance is a little bit more difficult to find because our speed is not constant. Our speed is changing. And so to know the total distance over a change of speed can be a little bit difficult. And so if we try to again focus on, or instead focus on this part of our graph rather as an area as opposed to this relationship of distance times time. So if we instead thought about it as area, where this is a right angle, the leftover dimension down here is 2, and then it still has a height of 8. So then that area is equal to 1/2 times 2 times 8, which is 8 kilometers. And that's how many kilometers that particle traveled, that object traveled for that 2 hours with a constant decreasing speed. So if we want to know the total distance, that total distance is 32 plus 8, which is 40 kilometers. So this is our bringing in the relationship that we know about speed, distance, time, the relationship that we know about velocity and time acceleration type of stuff, because we're getting to a placement here from a velocity equation. And how we do that is by focusing on the area. So that idea of finding the integral is you're finding the area underneath that curve when you're talking about a definite amount of time. Right? So here we've got a definite integral. We're going to explore this a little bit more just by doing a few experiments here. So what we're going to do is we're going to graph each of these equations, this equation, and then we're going to find the area underneath that equation, between that equation and the x-axis, between these integrals. So our first step is to just graph it. Remember that f of x equals 3, y equals 3, is just a horizontal line at 3. And if we're talking about a distance between 1 and 5, we're talking about this area underneath the equation and between 1 and 5. Okay, so if we wanted to use geometry to find the area of that region, this is just a rectangle. So your rectangle is base times height. So here we have a base measurement of 1, 2, 3, 4, and a height of 1, 2, 3. And so we have an area of 12. 12 what? I don't know, just 12. And then if we wanted to calculate the value of the definite integral of the function on the same interval, writing that definite integral out, you have that little integral symbol. We're going from 1 to 5 of this equation. And it's an equation of x. And so that's how we write the definite integral out, from 1 to 5 of that. Now that is just equal to, and we can find that integral. Remember that it's 3, and then you can just add on the x when there's no x there. We don't put plus c for our definite integrals because we realize, if we remember from our last lesson, that c ends up canceling out when we subtract our values. And so c is just kind of this redundant process that we add in and then subtract out, and it doesn't really matter with definite integrals. So we just leave out c when we're calculating the definite integrals. And so here's your general integral, your indefinite integral, and we're going to evaluate it from 1 to 5. Which means that we first plug in 5 for x, and then plug in 1 for x. Oops, and do not add them. We are subtracting them. So that'll be 15 minus 3, which is 12, which is the exact same thing that we just got above from just using geometry to find this area. So they're the same thing. Let's try it again. This activity might feel redundant, but it's a recap on graphing, on just, do you understand how to graph these things? It's also a recap on understanding what that area actually means. You're going through here and you're drawing it and creating those boundaries and filling them in. And when we get to more complicated equations, which we will, even in this lesson, being able to know where to shade is going to be important. And then also it's just like a really nice quick recap on how to evaluate indefinite integrals. So there's a lot of things that we're just kind of recapping in this. So just kind of lean into that if you're feeling like, why are we doing this? So 2x has a y-intercept of 0 and a slope of 2. So I go up like this, starting at my origin, and go up by 2 over 1. That's y equals 2x. And we are going to evaluate that area between 0 and 3. So this is our shaded area that we are caring about in this situation. Now, the area of a triangle is what? The area of a triangle is 1/2 times base times height, or base times height divided by 2. Totally fine, absolutely the same. In regards to the base is 3 and the height is 6. Which means that we get a total area of 9. If we were to then evaluate that integral, this is the integral from 0 to 3, of 2x dx. Evaluating that definite integral means we first need to find that general integral. Go ahead and find the general integral. The general integral for this guy, x would become x squared, and then we would divide by that 2, and so it would be 2 divided by 2, or 2 times 1/2, which would just be 1. So it just becomes x squared. And we're evaluating that from 0 to 3. Remember that we put 3 in first, and then subtract out 0. 3 squared is 9, minus 0 is still just 9. All right. 2 more practices. They are getting a little bit harder every single time. This one, we're going to build our axes slightly different because notice our boundaries are between -1 and 1. So I'm still going to, our lower axis, our lower bound is still our x-axis. So I'm still going to put my x-axis at the very bottom because I know I'm not going below that. But I am going to put my y-axis in the middle.